Good morning, everyone. As you came into the Zoom meeting this morning, you saw our civil discourse disclaimer, which everyone had to accept. I want to go through a few housekeeping rules this morning before Jane Sprell, our president, takes over. This is our October membership meeting with our speaker, Dr. Frank Gilliam, speaking on global warming, separating fact from myth. Please mute your microphones to reduce background noise. Your questions, if you will note them in chat. And when Dr. Gilliam is finished speaking, we will go through all the questions with him. Please note, we are live streaming in Zoom and YouTube, and the YouTube version of this meeting will be for your review tomorrow. All right. Okay, Jane, if I can turn it over to you.
Thank you, Joe, very much. The technical part of this is so important, and I appreciate your volunteering to do that. Welcome to our October monthly meeting for our members. And my name is Jane Sprell, and I'm the president for this Pensacola Bay Area League of Women Voters. The League of Women Voters, as many of you know, is a nonpartisan political organization, which means we don't support particular candidates or political parties. Instead, we encourage informed and active participation in government through voting. Our league is very visible, providing voter registration throughout the community throughout most of the year. And our position is that every eligible voter should be registered. In addition to voter registration, we are proud of the opportunities to educate and influence public policy concerning local, state, and national issues. This is accomplished through many programs and events that we hold throughout the year. Events like these Saturday morning meetings allow experts to address local issues of interest, and almost monthly, we also offer a hot topic meeting that is a focus on a current issue of interest. If you are not a member, please consider joining. We welcome women and men to become empowered voters and better able to defend democracy. A couple of announcements I'd like to make before we get started with today's speakers. One is that we have a hot topic meeting planned for next week. The title of the meeting is Are Voucher Scholarships Being Are Voucher Scholarships Being Exploited? And that meeting is on Thursday, October 21st at 6 p.m. The speaker will be Dr. Sally Bootson, Education Chair for the Tallahassee League of Women Voters. And she will guide us through that voucher system and help us to understand that a bit more. You can register for that meeting if you're interested in coming on our website, just like you did for this meeting. In November, our monthly membership meeting will focus on Escambia Children's Trust Fund. So please join us. It's in a Zoom format, and that's on Saturday, November 20th at 10:30 p.m. a.m. I'm sorry, not up that late. Let me tell you a little bit about our partnership program and introduce one of our partners that's here today. We integrated a national league policy focused on diversity, equity, and inclusion in our work. And developing partnerships with other organizations in the local community has been our primary goal. Our league members are very interested in how and which local groups are partnering. Those phrases, "don't reinvent the wheel" and "many hands make for light work," sound so simple. And so we are extending an open invitation to community groups who might be interested. Our Saturday meetings will always feature one of our partners. And today we are very happy to introduce you to BRACE. And that's an acronym that stands for Be Ready Alliance Coordinating for Emergencies. They are our partner for today's program. And I'd like to welcome Michelle Luckett, CEO of BRACE, and thank you for your partnership with the League of Women Voters. Michelle, can you briefly share the role of BRACE? And since we have limited your time today, maybe our membership can get involved as a partner with BRACE.
Absolutely. So first off, thank you for having me. It is refreshing to see so many folks up and at it early on a Saturday morning, talking about important topics that are key to this community. At the center of those conversations is, of course, the issue, because we live in a beautiful Pensacola area, is disaster resiliency. What are you doing to prepare for a storm? What are you doing when a storm happens? What are you doing to recover from the storm after it's been an event? And then what are the resources that are available to you in the community throughout the calendar year, whether we're in storm skies or it's beautiful blue outside? So Brace is a disaster resiliency collaborative that basically highlights those four areas: readiness, response, recovery, and resources. And so from a readiness standpoint, we run the Community Emergency Response Training Program in partnerships with organizations like the League of Women Voters around Escambia County to train our citizens on how to be of assistance to first responders, not to replace them, but to be of help. That training is done both online and in person. It is taught by individuals who are skilled in emergency response, and it's open to as young as 13-year-olds, and I think our eldest member that's gone through in the last year is 92. So it's for an assortment of ages to get involved. Then from the response standpoint, Brace sits with Escambia County Emergency Management in the Operations Center during an activation. So an activation could be for a hurricane, as most people associate it with, but it could also be for severe flooding or for a fire or tornado, or a man-made event like the oil spill. And so Brace is responsible for volunteers and donations. So having key relationships like with the League of Women Voters for volunteer engagement is vital to what we do. So we are excited about this chat this morning. And then from a response standpoint, we then also handle what are called points of distribution, where we're assisting with food and water distribution after an event. Then in the recovery phase, we run case management support programs for Escambia County residents who may have an issue closing the gap between their repair cost and the repair funding that's available. So we work with our nonprofit partners, which includes United Way of West Florida, Habitat for Humanity, St. Vincent de Paul, and multiple other funders, Salvation Army, to bridge the gap in funding to repair homes. So if you follow us on Facebook or Instagram, you'll see that we are constantly putting up success pictures and of homes being repaired and people getting settled, even now a year after the storm. And so then the last part of the resources, we have a wonderful cadre of relationships around the region as well as around the state and the country that allow us to bring resources here to Escambia County to support our residents in creative and unique ways that really stretch the nonprofit dollars to be the best stewards of the money that's donated to us. So again, thank you for the opportunity. I know we're under a bit of a time crunch today. If you're interested in volunteering with Brace, we would love to have you. Our website is it's three simple words: bereadyalliance.org, or you can feel free to email me at any point in time and I'll connect you with our volunteer coordinator. All right, thank you very much.
Thank you, Michelle. We are very interested to learn more about Brace. That's good. I have the honor of introducing our speaker for today, and I think it's going to be a wonderful program just from what I've heard beforehand. Dr. Frank Gilliam holds a Bachelor of Science degree from Vanderbilt University and a PhD from Duke University. He was selected as Professor Emeritus at Marshall University, where he spent 28 years as a professor of biology. He recently joined the University of West Florida as a biology professor, and this is how he describes his research career. He says, "I am a plant ecologist with broad interest in terrestrial ecosystems, from grasslands to forest. Although I have ongoing research on the effects of excess nitrogen on hardwood forest in West Virginia, My recent arrival at UWF reintroduced me to a forest type that I had studied for my doctoral research at Duke, the longleaf pine ecosystem. I am particularly interested in plant-soil nutrient interactions and factors that influence plant communities of the longleaf pine savannas, especially fire. Also related to the longleaf pine is an interest in a major disturbance for these ecosystems, tropical cyclones. We know about those. I'd like to turn the program over now to Dr. Gilliam. Thank you for being here.
Thank you so much for the introduction. Let me see if I can make this work. It says share screen. So let's see if that's sharing. Is that sharing? Now, I hope you don't see what I see has a lot of little slides on the left. That should be the whole thing, though. So
I see the shared screen.
okay, wait just a minute. How about that? That should you, are you just seeing the first slide there?
Yes.
Very good. Okay, thank you so much. Well, again, I want to thank you for the honor of this invitation and sort of the nature of this title, Separating Fact from Myth Regarding Global Warming. There's a lot of misunderstanding out there regarding the sort of the science of climate change. Some of that is just a basic misunderstanding or lack of knowledge of how climate works. But some of it, unfortunately, is actually a kind of a strategy of misinformation. And this is something that has been going on for quite a long time. The tobacco industry, for example, did this sort of thing regarding the effects of smoking and so forth. So it occurred to me, and a lot of this was from living in West Virginia for nearly 3 decades, that the energy industry, particularly coal in West Virginia, had a very active strategy of basically investing in both Republican and Democratic parties. So they were truly nonpartisan in their desire to kind of control the narrative on these kinds of things. So what I wanted to do was pick out 3 what I call myths, things that are out there that are really not true, and to sort of highlight what is actually fact from what is this misinformation. I like to always start with acknowledgements and not end with them, because I think thanking people is more important than anything else. And I wanted to first thank Dr. Enid Siskin for her invitation and her interaction with me regarding this topic. She's quite an asset to this community. Most obviously for most people is her work with the Eco Minute. And she actually allowed me to do a few of these. And let me tell you, they're not easy. And I won't quit my day job. I'm not really good at it, but I've got a few of them out there along this topic. But she also does really good basic research with UWF as well. I also want to thank all of you, not just for the invitation, but also for the work that you do. It's really important work to defend, really essentially defend our democracy, which seems to be under a lot of attack lately. So thank you for your work. I've always been honored to be involved. There was a very active chapter in West Virginia, and I work with them on some issues as well. So I like to, what I want to begin with, and I hope you don't get turned off by a bunch of graphs and things, but that's kind of the world I live in. And this is sort of not really a rhetorical question, but it's something I ask my students. If you see a graph like this, which looks at temperature anomalies, and that's a kind of a weird word. If you look at the 0 there on the y-axis, on that left axis, that's basically the long-term mean. And what you're seeing is anomalies or departures from that long-term mean. So from 1880 to about 1960, they were either below or at that average. But since 1960, we've had a very substantial and highly significant increase in global temperatures. So, the question I ask my students, is this evidence of global warming? And the really quick answer is no, it is not, because climate operates on millennial scales, not on decadal scales. So what we experience from one day to the next is really weather, and there's a big difference in those concepts. So it's tempting to say, yeah, this is absolute evidence of global warming because of the increase. Now that is a real increase, but again, we need to have better evidence, more evidence than this, that we have warmed our climate. What I want to do at the beginning of my talk is to get a little bit of the science behind things like the greenhouse effect and so forth. And it begins way back. And by the way, there's no quiz at the end of this. Don't worry about it if you're not remembering anything. But I guess it's being recorded, so you can kind of have access to this later on. But Svante Arrhenius was the first to elucidate the special properties of carbon dioxide with the ability to trap heat. And he was the one who first described the so-called greenhouse effect, where carbon dioxide and other similar gases not only have the ability, but the innate tendency to trap heat in the atmosphere. And the idea that the greenhouse effect, it was called that because if you're ever in a greenhouse, it's always warmer than outside. Just like in a bright but cold sunny winter day, your car is always going to be much warmer than outside. And that's because solar radiation goes through the glass and kind of is absorbed and re-radiates back out at a lower energy, a higher wavelength, and that is trapped by the glass. That higher energy is heat, and heat is trapped by the glass in the same way that these gases trap heat. So just, again, I don't want to be too sciencey here. I know this is a little early on a Saturday morning for all this science, but when I talk about solar radiation, it refers to the entire spectrum, all the way from the low wavelength UV radiation that has high energy, all the way to the high wavelength infrared. Now, infrared is heat. Those are synonymous terms. Infrared radiation is heat. What we call light, the visible part of the spectrum, has no heat at all. But this type of electromagnetic radiation can transform from one to the other. And so what's happening with the greenhouse effect is that the heat the solar radiation that's absorbed by the Earth's surface is re-radiated out at a higher wavelength, a lower energy, and that is heat. So a little bit of the science behind greenhouse gases. I'll go through these really quickly. They're all basically the same principle, but carbon dioxide is the one we talk about mostly. Methane is another one. Nitrous oxide is another one. Ozone itself is one, and even water vapor. And the reason they all do this, and I'm going to put their formulas here, is think of these bonds as being bendable. They're not all that breakable. In fact, carbon dioxide is an extremely inert form of carbon, but these bonds bend a lot. I call them being wobbly, and they're so wobbly that when they encounter infrared radiation, heat, in other words, they tend to wobble and it absorbs that heat. So it's not that they can absorb heat, they cannot help but absorb heat when they're in the atmosphere. So the non-greenhouse gases, thankfully, are nitrogen and oxygen. Here's their chemical formula. 78% is nitrogen, 21% is oxygen, and those bonds don't bend at all. So those do not absorb heat. And of course, as you can see, 99% of our atmosphere is these two gases. The other ones are lower concentration, but nonetheless very effective. So this is just a little cartoon that shows kind of how this works. You got solar radiation. By the way, see where it says sunlight? I got this from a textbook. That's wrong. The textbook has this wrong. It's supposed to be solar radiation. Okay, sunlight alone does not do this. It's the entire spectrum of solar radiation that does it. So again, the radiation goes through the atmosphere. It's absorbed by the Earth's surface, and it's re-radiated as heat. And that's that little squiggly red line. When it encounters carbon dioxide or any of the greenhouse gases, it re-radiates back to Earth as heat. That's the nature of the greenhouse effect. And I won't spend much time with this one, but carbon dioxide is actually the least effective greenhouse gas. Methane is 32 times more effective, nitrous oxide 150 times, and so forth. The main distinction is that carbon dioxide is the highest concentration. And where it says 400 parts per million, this is an old source. It's much higher than 400 now as we speak. So I got this, I found this from 1912. I did a fact check, and this is an actual clip from a newspaper in New Zealand that speaks of this in the bottom. It talks about coal consumption affecting climate. This is 1912 now. And it talked about it tends to make the air a more effective blanket for the earth. And this is enhancing the Arrhenius greenhouse effect. Look at this, what I've highlighted. The effect may be considerable in a few centuries. Keep that in mind now, the time thing, a few centuries. So I know that we're not supposed to be partisan, and I'm not making a statement here as a partisan statement. I'm making a statement as a scientist criticizing something that was incorrect, stated on the record by the former administrator of the EPA, Scott Pruitt. He said, I think that measuring with precision human activity on the climate is something very challenging to do. That's wrong. That we have extremely sophisticated instrumentation that can very accurately measure what we're doing to the climate. So the first thing is wrong. There's tremendous disagreement about the impact. That's another incorrect statement. There are some people who don't agree, but that doesn't mean that it's a tremendous disagreement. In fact, 90+% of scientists accept the fact of global warming. Now, you can say you disagree with it, just like you can disagree with gravity. It doesn't make it any less so. So he says, I would not agree that CO2 is a primary contributor to global warming. He's free to make that opinion. That makes it no less the case. We don't know that yet. Another incorrect comment. So this is just a series of incorrect statements stated on the record as the administrator of the EPA. So this is the kind of thing that we have to deal with, this type of misinformation. So are we getting more CO2 in the atmosphere? Absolutely. These are data going way, way back. And of course, at the time of the Second World War is when things really got ramped up in the late 40s up to the more current time. These are fairly old data, but the trend is still going up. Just to give you an idea, this is where that statement was made in 1912. And one of the things that the statement didn't take into account is the fact that there'll be more CO2 emissions in the future. So we get things like this. So I said I lived in West Virginia for almost 30 years, and we would get these columns, these syndicated columns. This guy named Thomas Sowell, I think that's how you say his name, and Walter Williams, they would have these columns, these syndicated columns, and these are economists that feel like they need to weigh in on science. They just don't know science. So this guy says that everyone can agree, for example, that the heat of sunlight is greater in the tropics. Remember, sunlight has no heat at all. So this whole thing is just an erroneous assumption. And anyway, so there's a lot of things wrong here. This is just to remind us that light and heat are different things. They're not to be equated at all. And this guy, Walter Williams, states that I, as a climate change scientist, is part of a socialist agenda. So apparently I'm a socialist. My parents would be so disappointed if they were still alive. So anyway, so this is the kind of misinformation that we're having to deal with. And what I'm trying to do today is dispel some of these myths. So let's begin with the first myth. And that is that we stupid environmental scientists have missed big time on the predictions. Have any of you ever heard of global cooling, that there was these predictions of global cooling that never happened? I'll tell you what never happened. Nobody predicted global cooling. That's just something that somebody made up. No paper was ever published in the peer-reviewed literature to predict that we'd experience global cooling. That was just set up as a straw man. That never happened. But let's go back to that first myth that we missed big time on our predictions, because that's what these columns say. They say that we missed on all of our predictions. So let's go back to the peer-reviewed literature. And in 1988, James Hansen, one of the leading climate scientists at the time, he's now since retired, made the first predictions in this paper. It's all scientific gobbledygook. I know it's really kind of not very interesting, but I want to point out or highlight what I think are the most important predictions. Number 2 there talks about the warming pattern should be clearly identifiable in the 1990s, and that the amount of warming should equal 3 standard deviations above the climatology of the 50s. In other words, okay, standard deviation is a measure of variability. And so he's saying that it'd be so much higher in the 90s and the 50s, it would be 3 times that. We'll find out if he was right. The second one is even more interesting in some ways, that he predicts here in number 4, that there would be a higher frequency of extreme events. So the cold getting colder and the hot getting hotter and the wet getting wetter and the dry getting drier. All of these extreme events become more and more frequent. So let's see if he was right. Well, this again is that same graph that you saw earlier. This is the 1950s, and this little blue thing is a standard deviation. And he predicted that by the 90s, there would be 3 standard deviation increase, and there we are. And we are continuing to increase to the present day. So to say that we got our predictions wrong is an absolute incorrect statement, that Dr. Hansen nailed it really accurately in terms of temperature. And what's related to that is the level of CO2. These are CO2 data actually measured on the Mauna Loa Observatory going back to the late 1950s by a guy named Dr. Charles Keeling. We call these the Keeling curves. Goes up and down, up and down, up and down. Those are the seasons of the Northern Hemisphere. But since Dr. Hansen made that prediction, CO2 has increased 15%. In fact, these are kind of old data. This little red dot is the current concentration. We're around 410 parts per million. And in our lifetimes, it'll never go down below 400. It's still going to be going up. So that heat trapping ability is always going to be accentuated as long as CO2 goes up. What about the prediction of extreme events? Well, this is from a paper I published a few years ago, actually about temperate forest ecosystems, but it has some data in it that I wanted to share that I think is relevant to this, whether or not the predictions were correct. So this looks at, and unfortunately we only have data that go back to 1980, but if you look at this orange sort of color here, those are droughts, fairly infrequent here, very frequent now. The opposite of droughts would be floods, fairly infrequent back then, much more frequent now. You can't get a better example of increasing frequency of extreme events than something like this. What are some other things that happen? Another thing that doesn't get out much is that global warming is enhancing or is altering the phonology of organisms. The phonology is a fancy word that just means seasonal change and seasonal patterns. Like when the leaves come out in the spring, that's phonology. When the leaves change in the fall, not around here, but up in the north, that's phonology. Phonology also describes the life cycles and the patterns of the life cycles of all organisms. In this case, this is from that same paper, and it shows that before global warming, this is a pine beetle. It's very destructive. It kills western pines, and it had what was called a univoltine pattern. That's a fancy word for meaning one life cycle per year. Nowadays, because global warming is making growing seasons earlier and later, it's extending the growing season, they're now able to have 2 life cycles per year. And any of you have had any math background, that's not times 2, that's to the second power. That's an exponential increase in the number of offspring. So this, what you're seeing in the background, that brown stuff, these are not deciduous trees. These are pine trees that are completely killed by this mountain pine beetle because of the greenhouse, of the global warming enhanced life cycles. I just had to throw this in here because I think it's so cool. These are data that are collected every year over in Japan. They're very meticulous about their record keeping. This goes all the way back to the year 800, and it looks at the peak of blooming of the cherry blossoms over there in Japan. And of course, there's a lot of variability from one year to the next. But if you look at this solid line, it's kind of a smoothing curve. And sure enough, from 1800 to the present, these cherry blossoms are peaking earlier and earlier and earlier. I don't know if any of you have been to DC for the Cherry Blossom Festival. It's the same thing here. The cherry blossoms are blooming earlier and earlier in DC every year for this exact same reason. Big The headline right, every summer, it seems to be, is the number of fires, these disastrous fires that occur. Now, fire is a beneficial factor in some ecosystems like longleaf pine. What I'm talking about here are these conflagrations, these really large scale, intense fires. And again, the data we have, the best data go back to only around 1980 to the present, but again, a highly significant increase in fire frequency over the same time period. So, did we get it wrong? I would say that's an incorrect statement to say that we did. I think we got it right. So myth number 2, how many of you heard of this? That the climate is always changing, but it does so in cycles. Currently, CO2 are going and temperature are going up, but they'll go down again. Well, for this, that we need longer term data than just a couple of 100 years. Fortunately, scientists have discovered a way to do that, and what they do is to take ice cores in the polar regions. Particularly, this is the Lake Vostok study. Here's Antarctica here. This little rectangle is a focus on this. You can see this is Lake Vostok. This is the top part of it. The lake itself is fresh water at the very bottom of the core, and you can see this is actually fresh water here in this lake. This is about a 3.5 kilometer, 3.6 kilometer. It's about what is that, like 5 miles or so of depth. They take a core of ice. Now, any of you who used to make your own ice, like you put an ice tray, you put water in the ice tray, put it in the freezer, it comes out and it's got these little white things. That's not pollution. That's actually just air bubbles that try to escape at the very last moment before freezing. And the air that's trying to get out is indicative of the chemistry of the air at the time of formation of the ice. So what they do is they take these columns of ice and they melt them and they get the air out of the ice and they analyze it for all of these gases, carbon dioxide, methane, nitrous oxide, and so forth. And what we get is a record that goes back almost 1 million years. So the deniers of global warming are actually correct, even though they didn't realize it, in that there are cycles, and these cycles repeat themselves about every 100,000 years. There's a lot of reason for that I don't have time to go into, but basically, CO2 has gone up to about 280, down to about 180, and it repeats that every 100,000 years for the longest time. We are currently nowhere near in that. We are now at 407. This is 2018. We're a little bit higher than that, but we have not been in this 100,000 year cycle for ever since basically the modern age of the Industrial Revolution and so forth. So the cycles occur, but they're no longer occurring. We're no longer in these cycles. And so all sorts of things are related to this. This is from a paper that I talk about with one of my honors classes, where mean sea level is rising. You can see that here. Arctic sea ice is going down. You can see that here. Heat content, that's really important, by the way. We'll talk about tropical storms in a moment. That's really important in driving those related to temperature and so forth. So lots of these factors are related to increasing CO2 and greenhouse gases in our environment. So I did want to talk a good bit about tropical storms. The fancy word is tropical cyclone. They have different names for different intensities. A tropical storm is the level at which it gets a name. And higher than that is a hurricane, and you have category 1 all the way through category 5. Anything that's category 3 and higher is considered a major hurricane. I don't know if anybody can guess what this is. This is actually Katrina back in 2005, which at some point gained category 5 status. It hit at category 4. And I would just say, in a practical sense, it's just splitting hairs. They're both very, very destructive. This is to show you how busy last year was. Last year was one, literally for the record books. We had over 30 storms. This shows you the track of all of those storms. Notice that thankfully, most storms do not make landfall, but we had several that did, and they were highly destructive. This one with the little white here, this is the one that's most near and dear to us. This is Hurricane Sally that hit us last year in September. Currently, we're pretty much right on par with that. We have now up to the V storm. The next storm is Wanda. Fortunately, I've checked this every day. We don't have any indication that that's happening. Most of the storms, if you see these little islands here, these are the Cabo Verde Islands. And we call these Cabo Verde storms because most of them will start here. But you also have some destructive ones that begin here in the Gulf or off of the Caribbean and so forth. But I thought what I would do is show you that they make these names. And when I was a kid, I remember all the storms had female names. And I don't know what. I guess probably women got tired of being blamed for all this destruction. And what about guy names? So several years ago, NOAA decided to alternate male names to female names or whatever. So back in 2018, Alberto, then Beryl and Chris and Debbie. Then it was Andrea and so forth. So this is the last several years. Those are a lot of storms. And of course, we went beyond, in 2020, we went beyond the W storm into the Greek alphabet, alpha, beta, and gamma, and so forth. As I said, currently we've had Victor. We haven't had anything since then. That's still a lot of storms. I'll talk about some data in just a moment. So how storms form, I don't want to get too much bogged down into the science of it, but just please know that a lot of factors go into creating a tropical cyclone. But the main driver, what we call the heat engine, is right here in number 3. That seawater that's 27 degrees Celsius, that's about 81 degrees Fahrenheit and higher, indicates enough heat in the surface water that when that heat is released, it rises, it creates this very low pressure center in the middle, and that's going to draw air into it. If you look up at number 1, that is called the Coriolis Effect, and that's based on the fact that the Earth is spinning, so that in the northern hemisphere, the Coriolis Effect is going to divert wind that goes into the middle of the center to right angles to the right and create a counterclockwise pattern. So if you look at any tropical cyclone in the northern hemisphere, it's always going to go in a counterclockwise direction. In the southern hemisphere, it's the opposite. These all go in a clockwise formation because the Coriolis effect is equal but opposite in the lower hemisphere. Other factors, number 6 here is basically referring to high humidity. Humid air has much more energy than dry air. You might remember way back in May, we had a bunch of storms at the beginning, and then there was a long period of no storms. That was the result of a plume of dust that came off the Sahara Desert and made its way all the way to the middle Atlantic. That was very dry. Dry air sucks a lot of energy out of these formations. And so that's part of it as well. So a lot of these factors go into play, but the main driver is the temperature and the heat content of surface water. So just to show you, this is a paper that was published earlier this year that focused on the effects of tropical cyclones on longleaf pine forests, but it had a lot of basic information. So these are storm tracks that go back to the beginning of our records for the Atlantic as well as the Pacific. And you'll notice there aren't any here at the equator. The reason why is there is no Coriolis effect roughly 400 or so kilometers north and south of the equator. That's about 300 miles. So if you get really close to the equator, you can't get a tropical cyclone because you don't have enough Coriolis effect to create that spin. But here again, these are the Cabo Verde storms that go this way. And notice that these storms are they form here, but they basically die somewhere around here. The reason why is you have the California current bringing really cold water down here. So they basically just form here and they die in the middle of the Pacific because there's just so little heat to drive the system. Over here in the Asian waters, they call them typhoons. I'm not sure why, they're different kind of thing, but notice there's a big gap here, and the reason for that can be seen here. If you look at ocean temperatures, and here's where we are, really warm here. This, I think, is in July of a couple of years ago. This is basically just like a hurricane alley, if you will. Once they form here, they can get easily into the very warm waters of the Gulf. This by here, by the way, this is a good example of what the Gulf Stream looks like. But if you look at the bottom figure, you've got the South Atlantic gyre here, you've got the South Pacific gyre here, and so forth. So you basically get no hurricanes form, tropical cyclones form on the west coast of most continents because of these cold gyres that come up and down from polar regions. So let's get back, same paper. Earlier you saw data that looked like this. This is this blue line, the blue dots, and the black line are the air temperature. Green is the ocean temperature. And remember that that's the driver, the main driver in the formation of tropical cyclones. So it is going up significantly as well. You've seen this kind of thing before. This is from NOAA, and it shows you that the hurricane season starts around May, ends in the end of November, and that fortunately for right now, statistically speaking, we're over the worst, but things can still happen. So far, not a lot in the current forecast. So these are just actual data that I got from the archives of NOAA, where the National Hurricane Center does its work. And you can see that there is indeed a highly significant trend line going from 1850 to the present. This little squiggly line is called a 25-year running average. So each point on this line is an average of the previous quarter of a century. And there's a lot of squiggle here, but for the most part, since the year 2000, we have had a significant increase in the number of, these are the tropical storms. These are not the higher intensity ones. For those, we have a little bit of a different pattern, but still a significant increase over time. The black dots are hurricanes. The open dots are major hurricanes. And as you can see, there's some years that we don't get any major hurricanes. That's not happened recently. We've been getting major hurricanes every year since around 2000. But again, these trend lines are highly significant in a statistical sense. So we're getting more hurricanes and more intense hurricanes over time. And one last thing, I think, and then we'll move on to some other things. I was interested in just, okay, what is typical? Remember the idea of new normal? Well, from 1850s to about the 1920s, the black column here, that's indicative of the annual number of tropical storms per year in a given decade. So there was roughly between 6 and 8 tropical storms per year for the 70-year period to the 1920s. Let's just cut to the current position. From the decade of the 2000s and the 2010s, we've averaged 15. So that's over double, maybe even close to tripling the number of tropical storms. The other extreme is the major hurricanes. Those were very rare a long time ago. We now have at least quite typically 3 to 4 or so major hurricanes. In terms of just hurricanes, they're going from 4 to about 7 or so. They're close to doubling. So it's fairly clear that both number and intensity are going up. Again, from the same paper, you might be interested in knowing that Florida, and not surprisingly because of its location and its shape, gets the highest frequency of landfall. Now, again, let's go back. This is number of storms formed. Not related to landfall. This is now the number of landfalls, and this is the redder, the higher the number. Obviously, you can see that the southern tip of peninsular Florida gets the highest. Just to put some numbers for Florida, not surprisingly, Miami-Dade, Broward, Monroe County have the highest. Here we are, Escambia and Santa Rosa. We're about half, but still pretty high in terms of numbers of landfalls over in the past 100 years. So another thing, and we can come back to that in a moment about tropical cyclones, but another very serious effect of global warming has been the melting of permanent ice. And this is in the Arctic, the Antarctic, but also glaciers, the melting of glacial ice as well. So this is just a photograph of Antarctica showing a lot of recession of ice coverage there. And of course, that leads to increasing sea level. I don't know if any of you have been to Boulder, to Glacier National Park. When it was first founded, it had somewhere over, well over 100 glaciers, maybe 140 glaciers. Currently, there's only 20 glaciers left in Glacier National Park, and the model projections is there will be no glaciers in Glacier National Park probably in the next 50 years or so. I'm not sure what they'll call it because they won't have any glaciers, but in 1932, this is what Boulder Glacier looked like. This is what it looks like today. Here's the Grinnell Glacier here up here in 1910. Here it is currently, or somewhat currently, 2008. This is another view of the Grinnell Glacier here. So another myth, you may or may not have heard this, but there was a letter written to the Huntington paper that said sea level rise cannot be occurring from the melting of polar ice, because when ice water melts, the water level in your glass does not change. This is the correct statement, that if you put an ice cube in a glass of water and let it melt, the level of the water will not change because the volume of displacement of the ice cube is going to be replaced by the volume of the water that melts. What is erroneous about this is the idea that polar ice is floating in the ocean, and it's not. It is perched on land. So here's another view of that Lake Vostok research. There's bedrock. And so when these big chunks of ice break off, they're coming off of bedrock. And then when they melt, yes, that's causing sea level to rise, and it's rising very significantly. That's another concern for the state of Florida. We have the second lowest mean elevation of any state in the United States. Now, one of the things that I would always do with my class, my ecology class, is we would talk about these environmental problems. And way back in 1990, when I first started at Marshall University, I had to leave my class with a very bleak outlook. There was very little that I could say that was really very encouraging about the future. Fortunately, in 1970, something happened, a very important piece of environmental legislation that has actually I use as an example of what I call an environmental success story. There we go. So this is success story number 1. And it is called the Clean Air Act of 1970. And I would somewhat rhetorically ask if anybody remembers who was president in 1970. That would be none other than Richard Nixon. Now, at the time, he had a lot of pushback from his party to say, oh, you can't sign this because there'll be an economic collapse. The economy will not be able to survive the Clean Air Act as it is proposed. Now, the initial target of the Clean Air Act was the so-called acid rain. I don't like that term because it's more than just rain. It's all sorts of different types of deposition of acidity that was impacting both terrestrial and aquatic systems like forests and streams and things like that. So the initial target was sulfur emissions, that when we burn coal, all the sulfur in the coal gets oxidized to sulfur dioxide. When that gets into the atmosphere, it becomes acidified, and when it rains, all that acidity rains down on our natural ecosystem. So the initial target was sulfur emissions. Now, again, the initial pushback was it's going to wreck the economy. We can't enact the Clean Air Act of 1970. It's going to wreck the economy. Well, let me first point you to the blue line at the bottom. This is the number of pollutants removed since 1970. We've had a 75% reduction, highly effective legislation. But what about that tanked economy? That's the green line. I'm not saying tanking at all. In fact, we're doing better than ever. And so what the Clean Air Act did was to actually increase markets for clean air products and things like that. So the idea that fixing the environment is going to crash the economy is just not correct. It's just not true. Now, what I wanted to show you, and I think you'll enjoy this, I certainly like looking at it, is a series of about 25 or 30 slides. It's kind of an animation. Chemically, acidity is a hydrogen ion. Hydrogen ions create acidity. So what you're going to see is a map of the United States. It's going to start let me see, what was it again? Yeah, in 1986, going toward close to the present. The redder, the more acidic. The greener, the more neutral, or the cleaner, I guess you could say. So take a look at this animation from 1986 to close to the present. And the red is indicative of acid deposition. And note, by the way, where I was in West Virginia, about right there in my research for the longest time, and that's part of what our research was. It doesn't take much to see that things are getting better by the year 2000. They continue to increase in improvement. So by the year 2012, in other words, the Clean Air Act was highly effective. It did not wreck the economy. Something else, lead in the environment, lead in paints, but particularly lead in gasoline. This is a study, it's an old study, I apologize for that. But here they did snow coring in Greenland, and they were able to backdate that. So here's sort of historical levels of lead. There were no sources of lead, so there was no lead in the snow at 800 BC. Here, this little part of the curve juts up. This is where the petroleum industry discovered that if they add lead to gasoline, it burns more effectively. And so that introduced lots of lead in the environment, lots of problems associated with lead toxicity, especially for human health. So when they enacted the Clean Air Act, another target was lead in the environment. That's why we now have unleaded fuel and have been that way for quite a long time. These are, again, not very current data, but it shows you a good trend that here's the lead consumed in gasoline. Because of the legislation, it's now gone way, way down. The ambient air concentration of lead also way down. Is that having effects on humans? Absolutely. Here's the lead used in gasoline. And here's the average blood lead levels in humans also going down. So another benefit from the Clean Air Act. The second one, and we'll be done. I don't mean to be going too long here. That the second success story has to do with chlorofluorocarbons. These are an entirely artificial set of compounds that are basically methane with a one carbon atom with a bunch of fluorine and chlorines. They're extremely efficient at trapping heat. And so they're really good for coolants and foam products. So like freons, these are good examples of CFCs. And when they were invented, they were thought of as this miracle compound because they were so efficient. You could use those in refrigerators. Before that, you had to use ammonia, which is extremely toxic and inefficient. So they really kind of really changed life as we know it quite a bit. And unfortunately, in a bad way, because they're very stable compounds in the troposphere. That's where we live. We live in the troposphere. But when they go out into the stratosphere, they get broken down into chlorine atoms, and those chlorine atoms break down ozone. And that's the protective ozone that protects us from UV radiation. And that's the very, very harmful radiation that can cause skin cancers, melanoma, and ultimately death, actually in some extreme situations. So it was made available or made aware that the major producers of CFC, those are pretty much the major economies of the world, were creating this problem. So this is a really old graph that shows CFC production going back to 1950. It went up. And by the way, this flat line was the oil crisis. And it takes a lot of energy to make CFC. So this flat line was not environmental improvement. This is basically the economy crashing and so forth. And then it went up again. But these major producers, United States, Europe, and so forth, got together in Montreal, and they passed what's called the Montreal Protocol. Who was president in 1987? Anybody remember? That would be Ronald Reagan. And again, he got a lot of pushback from his party not to sign up with this, but he got a lot of good information. And this is a paraphrase, not an exact quote, but he said essentially, the science is good. The science on CFCs is good. Let's trust the scientists. And how refreshing that was to hear that, because we don't hear that much anymore. But notice almost immediately, emissions production went down because of the protocols. We signed on to it. And here is a more current set of data that CFC production is now essentially zero because of this global cooperation. So I think the point here is We can use both of these as models of how to address global warming. We do not lack the ability to fix this problem. We just lack the political willpower. And it's, as a scientist who knows the background story, know that we can fix this. It's just very frustrating. This is a pretty interesting modeling figure. It shows how many deaths have been avoided or averted because of the Montreal Protocol. We can use what we learned about acid rain and about CFCs, apply that to CO2 emissions. We're not going to wreck the economy. It didn't happen for acid rain. It's not going to happen for CO2. So with that, I'll finish. There was an old tradition at Duke University to end with a sunset. So this is a sunset taken by my son, Ian Gilliam, who at the time was a midshipman at the U.S. Naval Academy. This is Chesapeake Bay. And by the way, I should have updated this. He's not a lieutenant junior grade. He's a full lieutenant now. But this is something that's more hopeful. This is sunrise over Pensacola Bay, and I will leave you with that. And thank you so much for your time and your patience. Thank you. So I guess I should unshare or.
That would be great.
Okay. So stop share. There we go.
Okay.
Thank you. That was most interesting. And I'm sure we have some questions for you. And so, Joe, I'll turn it back to you.
Okay, and I will throw that out to our membership. Mary Gutierrez, if you have read her chats, has been very supportive of science research. Does anyone have a direct question for Dr. Gilliam? Okay,
I have a question.
Yes.
Yeah, so we are seeing an increase in hydraulic fracturing, which of course emits carbon dioxide as well as methane. So it's sort of going in the opposite, or it is going in the opposite direction of addressing greenhouse gas emissions and dealing with climate change. What can we do to stop? I mean, I know you said it was political, but we're going in the wrong direction, I guess is what my point is. And I know it's a political will, but what can we do for the non-science people? I am an environmental scientist, but I work with non-science people. But what can they do to push for us to move away from hydraulic fracturing and actually significantly address the issues associated with climate change and the activities that are exacerbating this issue?
Okay, that's a really good question, and I'll address it on the most general way. Any strategy that pursues fossil fuels is going in the wrong direction. So the fact that what they're trying to get is natural gas or whatever it is, that's still a fossil fuel. Fracking is bad in so many ways. It also really, really pollutes the groundwater. And that to me is almost as concerning as anything. People have asked me, well, what about ethanol? Ethanol is clean. It's not going to make acid rain like coal does, but it still makes CO2. Our future has got to be no fossil fuels. But it's really a simple. It's okay. What I tell my students, what is simple is not always easy. It's simple that we just need to move away from fossil fuels. There is no other argument that could be made. We have to get away from fossil fuels. That's not an easy thing to do, but it's a very simple kind of approach. And so when it comes to the fracturing, it's just that's not a good idea. I think but again, it creates even more problems than the obvious ones.
All right, thank you for that.
And a follow-on question here is, any thoughts about nuclear?
Nuclear is really bad, really bad. What are you going to do with the nuclear waste? Well, I think we tried that. It doesn't work very well. You have to cool the towers. That heats up the water. That really destroys aquatic ecosystems. Hot water does not contain very much oxygen, so hot water will kill fish. So nuclear is not a good option. I think there's so many things that we can get into. I think between solar and wind, again, I think what can be done there is to provide incentives to improve the technology we have. The technology is good, but it can be better. How can you make it better? How about tax incentives and things like that?
Dr. Gilliam, have you presented your findings to any local political leaders?
Yeah, well, I kind of can't do that. There's kind of like these rules at UWF that I'm not allowed to do this. So I have to go through them. And for some reason, UWF didn't think that my paper was newsworthy. So they never wrote this up. You're the only people hearing this, by the way. The paper that I just talked about, the one that talked about tropical cyclone formation and longleaf pine, I tried to get a press release out there. Nobody at UWF thought it was newsworthy. And apparently, according to them, the P&J didn't think it was newsworthy either. If you all have any connections, I would like to get this information out there. People need to know this stuff, that global warming is increasing in frequency and intensity of tropical storms. People talk about how much it's going to cost to fix the problem. How much is it costing us that we have the problem? How much did it cost you for Hurricane Sally? We're still paying things off. And that was just one storm here. In Louisiana, they got hit multiple storms. Sorry, I'm getting a little preachy here. I'll have to.
And another question, what are your thoughts on the water wars worldwide that are caused by climate change?
Yeah, that's a good question and a really serious issue. And that's tough to deal with. We are warming the climate in such a way that the atmosphere holds more water vapor. So we're not creating or destroying water. You can't. That's part of the laws of thermodynamics. But we're transferring usable water for us that we need in our aquifers, in our groundwater, in our streams, in our lakes. We're transferring that up into the atmosphere, which, by the way, if you remember, water vapor is a greenhouse gas. So more water vapor is less water that we can use and more trapping of heat. So we call that a positive feedback. Now, the word positive sometimes means a good thing. In this case, positive feedback means that if you push on your brakes on your car, it speeds it up and not slows it down. Negative feedback is what we need to have a negative feedback, because that's like brakes on your car.
Dr. Gilliam, I think we've come to the end of our questions, but in case you're not seeing chat, somebody wrote that this was an excellent presentation. Best I've seen on climate change and impacts. Thank you.
Appreciate the kind words. And I really enjoy this opportunity.
Okay, what a great presentation. And I feel like people in our group may have other networks that they can recommend contacting you so that the word can get out. I'm just very, very impressed by what I've learned because I'm on the level of Bill Nye the Science Guy. So
well, he's a good guy.
To understand better what's happening. And thank you for spending your Saturday morning with us.
According to my wife, I'm full of it. So you guys got some of that. So that's good.
It was very, very good.
Jane, if I can interrupt for just a minute, there was a question of how do we get a copy of this presentation? And of course, the presentation itself will be on YouTube video. I'm not sure if the question is really, can we get a copy of this PowerPoint? I
can send you the PowerPoint if you want.
That would be great, and we could distribute it to the members.
Why don't you send me an email requesting that, and I'll just reply with a copy of the PowerPoint.
We can do that. Thank you.
I also want to thank Michelle for coming from Brace and letting us know about that program and what they do in our community. Thank you so much. Anything else? Thank you to our guests. I think we had guests that came today to this meeting, and to our regular members who are here. And as always, we invite everyone to be an active part of the League, and we appreciate so much the manpower, woman power, whatever you want to call it, to assist us in trying to get education out into our community.